Today, we want to start looking at functions of 3 variables and what we can use to picture those functions. How can we visualize those functions? So this is just going to be one step further than our looking at functions of 2 variables. So let's recall what we did. We know that we spend a lot of time studying functions of 1 variable. When we have y equals f of x, we are thinking of a 1-dimensional curve in R2, 2-dimensional space. When we increase that by 1 dimension, we write z equals a function of x and y, and we end up with a 2-dimensional surface in R3. So we have a 1-dimensional curve in R2 for a function of 1 variable because we're only plugging 1 input in. And so for each input, we have a height above the x-axis. We end up with a 2-dimensional surface when we have a function of 2 variables because we're putting 2 values in, and functions just give you the height above your inputs. In this case, your input is the xy plane. And so if you put a bunch of heights above the xy plane, you're going to end up with a surface. Now, this is a 3-dimensional thing. It's sitting in 3-dimensional space. One of the ways that we can picture this object, one of the ways we can draw a graph to analyze this object, is to look at level curves. So we can analyze the surface using level curves. So we're going to picture the surface using level curves, where f at xy is equal to some constant. I'll use the mortal constant in this one. We're going to picture the surface using level curves. We're going to take the function f of xy. We're going to look at a fixed value of z, and we're going to end up with f at xy equals k. This only has 2 variables, x and y. So now we're looking at a level curve. So this technique is going to rely on our knowledge of what a bunch of curves look like. Fortunately for our heroes, we've spent the last 12 years studying all kinds of different level curves. So when we upgrade this with 1 more variable and we write a function, I'm going to use w. So if w is the function of x, y, and z, everything goes up by 1 dimension. Our graph will be a 3-dimensional solid. And this will be in R4, in 4-dimensional space, because we have 4 variables, w, x, y, and z. What we're doing is taking each point x, y, and z, and w is the height above that point. Now it's hard to picture because it's hard for us and our puny 3-dimensional minds to draw 3 dimensions and then have a height that is perpendicular to all the other 3. Easy to picture things up to 3 dimensions because that's what our puny brains are. That's what our puny brains have experienced our whole lives. But now we have to picture an R4 where we have to find something perpendicular to left and right, forward and backwards, up and down. Now we need a 4th one that's perpendicular to the other ones. A lot of times students will want to suggest time. I don't know why we always go for time instead of temperature, but what if we need another distance? What if I need meters, 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 and meters, and not seconds? Or temperature. We can make a function of 3 variables by graphing the temperature at any point. It's not hard to come up with what a function of 3 variables could be. We're tasked with how we can picture it. So what we can do is, unsurprisingly, the same thing that we did before, because that's all we ever do in math. We just do the same thing that we ever did before, and we adapt it to the new scenario. So we're going to picture the solid in slices. We'll picture the solid using level surfaces. Where f at x, y, and z is equal to some constants. So looking at level curves, required us to be familiar with lots of different curves. So this required us, we need to be familiar with lots of different curves. And we do. So you know things like parabolas, equations of circles, equations of lines. You know about graphs of polynomial functions. So we need to know lots of curves. We need to be familiar with all those graphs. Certain things need to happen. When you see a function where y is to the first power and x is to the second power, you should start thinking parabolas. If they're both being squared, x squared plus y squared equals a constant, you need to be thinking circles. If x and y are both to first power, you need to be thinking lines. If x is to the first power and y is to the third power, you need to be imagining cubic functions. So you need to be familiar with all your curves. So now that we want to try to picture 3-dimensional solids in R4, we need to know lots of surfaces. So now we need to know lots of surfaces. Now we need to know lots of surfaces. A great place to start looking at surfaces in your textbook on page 691, this is in section 12.5. You have what's described as a catalog of surfaces. What's going on in the catalog of surfaces is we're really looking at variations of conic sections. We're trying to put conic sections together. So parabolas, ellipses, hyperbolas, and circles in different combinations. So that's kind of what the catalog of surfaces is built on. So some of the surfaces that you should recognize and how you should categorize them. I will drop a screenshot into the chat. So you can look for it later on. So here's what what the catalogs of surfaces starts to look like. This is the first three of several. But what we want to start associating is looking at an equation and then seeing what shape that equation will produce. So here are some surfaces. Once again, these are going to be things that not just we can think about for as two-dimensional surfaces in R3. That's what we're going to be looking at. But we want to imagine these as pieces of a three-dimensional solid in R4. And we can look at level surfaces where we hold W to be constant and come up with a surface. So we need to learn some surfaces, and so that's what we're going to do. Some surfaces that we should be familiar with. We don't have to be very good at drawing them, partially because I'm not very good at drawing them. But one of them, let's take a look at an elliptical paraboloid. So the equation for elliptical paraboloid looks like Z equals x squared over a squared plus y squared over b squared. So what this looks like is if we take a parabola and wrap it around and spin it around in an ellipse. So we can see slicing this parabola horizontally, parallel to the xy plane, produces ellipses. Slicing it vertically is going to produce parabolas. In this case, the z-axis will be, since z equals x squared plus y squared, the z-axis is going to be the vertical one. And then the y-axis and x-axis are going to be in their standard places. That's going to be the floor, and above the floor we have this big paraboloid. The elliptical part is going to be the round part. So looking at it from the top down, we see ellipses, and looking at it from any side view, we see parabolas. But since it's a solid or a surface, excuse me, it's a surface, we're looking at paraboloids. We can make a circular paraboloid if a squared and b squared are equal. If a equals b, we get a circular paraboloid. So if we encounter a function where we have an x squared and a y squared with the same sign and a z with a different sign, then we can think of the level surfaces as these elliptical paraboloids. If we take a solid, we can slice a solid into surfaces. We can do that Shrek style and picture an onion. An onion is like a sphere, a solid sphere made up a bunch of spherical surfaces. And that's all we're doing here when we're talking about level surfaces. We can imagine a solid where we have a bunch of smaller and smaller elliptical paraboloids inside each other. So we can imagine this as being part of a function. Let's say f of x, y, and z could be x squared plus y squared minus z itself. X and y are both squared, z is to the first power, x and y have the same sign, z has the opposite sign. So imagine this is what one slice of a solid looks like. Any questions?
What does the a squared plus b squared do to the shape itself?
A squared and b squared will just determine the left and right and the front and back distances in the ellipse. So recall that an ellipse will just be a fixed value of z. So an ellipse will look like x squared over a squared plus y squared over b squared equals 1. And so an ellipse is just a squashed circle. I mean, it's squashed in a very particular way, but in the x, it's like we have two radii. Once there's two of them, it's not a radius anymore. I know that, but it's like a circle with a radius and a horizontal radius and a vertical radius. So this point will be at a 0, and this other horizontal point will be at negative a 0. The bottom will be at negative b 0, and the top will be at positive b 0.
Got it. So a and b are the values of the edges.
Yeah, a and b are like how wide it is. When we have when a and b are the same, then we get a circle because it's the same all the way around.
Thank you.
So this is what everything's going to look like if we think of this surface and imagine the level curves of this surface. But we need to be able to picture the surface so we can imagine this as a level surface of some solid. We can imagine a solid sphere as a bunch of smaller hollow spheres stacked inside each other, like an onion. Thank you, Professor Schreck. So an ellipse happens when we have x squared and y squared and they both have the same sign. If one of the signs is different, then we get a hyperbola. So if I change one of these signs, yikes, walking and everything. So notice what we've done here. We've taken our elliptical paraboloid, and now instead of parabolas that both open up, z equals x squared and z equals y squared, now I have z equals negative x squared, but z equals positive y squared. So in the y direction, our parabola is going to go up, but in the x direction, our parabola is going to go down. So this is based on the curve, a hyperbola. A hyperbola happens when we make one of the values negative, or one of the x squareds and y squareds negative. So hyperbola would be like negative x squared over a squared plus y squared over b squared. So now in the So for an elliptical hyperboloid, in one direction, we're going to have parabolas facing down. So for constant values of y, once again, using our technique of looking at level curves, if I fix a constant value of y, z is negative x squared. So I actually need to put it over here. I also need some negative z. So if I pick a fixed value of y, I'm going to get z is equal to minus x squared. So I'm going to have, I need parabolas where z is a function of x. So instead of just parabolas going up, I need a parabola going down in the x direction. But if I fix the value of x, the parabolas are going up in the y direction. So we're running into a little difficulty in picturing it because I've squashed one dimension out of it by trying to draw it on paper. I need that Tony Stark interface where everything's like all three-dimension and hologram. I haven't seen footage of them filming that scene where all the computer graphics are not there, and it's just Robert Downey Jr. like waving his hands. Did the same thing in Minority Report. Tom Cruise just kind of like standing there moving his hands around. Any questions? So if A is 4 and B is 2, then you are correct. It's going to be wider. The parabola will be wider in one direction, and we'll have a skinny one up above. I hesitate to draw the whole thing, but at each point along this z equals y squared, I'm going to be drawing another parabola going down. And also at each of these points on this parabola going down, there's going to be another parabola going up. So what this looks like is a saddle. Sort of. Any questions? These are just a few examples. Yes, the saddle, the elliptical paraboloid is 12.83 in the screenshot that I sent. So the things that you want to look for in this catalog of surfaces is what happens when we get the elliptical paraboloid when x is squared, y is squared, but z is to the first power. And the x squared and the y squared have the same sign. The elliptical hyperboloid, the elliptical part comes from the hyperboloid part comes from we have a negative x squared and a positive y squared. That's the it's based because this is based on a hyperbola. So what you want to do is go through the catalog of surfaces and sort out what features of the equation produce features in the graph. Start making an association between features in the equation and features in the graph. So the other category of surface that you have to look at is where x is squared, y is squared, and z is squared. Then start thinking about what happens if you change the sign of x, y, or z. Any questions? All right. The other thing to remember is that we want to we need to put all these things, we need to imagine these as pieces of a solid. This is a surface sitting in a solid. So when we're thinking about level surfaces, think about a ream of paper. A ream of paper is a rectangular solid made out of a bunch of planes. We just take a bunch of planes and stack them up, and we end up with a rectangular solid. So that's what we're looking at. All those planes are different z values for some linear function. So another way to think about this, a ream of paper is that how you spell ream for ream of paper? Each sheet of paper is a level surface. I get to use this one. Eventually paper is going to go away. And so some old teacher is going to be like, oh, a rectangular solid is like a ream of paper. And then students will be like, oh, what's paper? And then the teachers will be like, oh, well, back in my day, we used to have to chop down trees and grind them up and flatten them out. And students will be like, oh, why don't you just use screens? Back in my day, we didn't have any holograms. I'm wondering if hologram teaching will come about in my lifetime, which would be great because then I could just record all of my lectures, even if they're in person, and project a hologram. So I could be sitting on a beach somewhere with an ice cold beer and then just like have the hologram in the classroom. That would be excellent. And then I would want everybody to have this. So it could just be a room full of holograms. And then someone would walk in and it's like, oh, why do you have a room full of holograms? This seems excessive. And then we'll be like, oh, dude, we had a really big special effects budget. And then they'll be like, all right, carry on. Any questions? Comments? Snide remarks? I don't know anything about holograms. Clearly. Well, there's budget-wise for movies, and then there's budget-wise for a school. So keep in mind, there's budget-wise for school. There's like teachers who, as a society, we're recognized don't make a lot of money because we know education is not important. And we make them go buy stuff. You know what I mean? I know we like to say as a society that we think education is important, but let's face it, if we really thought it was important, we would pay for it. We would say, this is important. Let's pay for it. We don't have a shortage. When we have a teacher shortage, it's not because there's a shortage of people who are willing to be teachers. There's a shortage of money that we're sending the teachers' way. So that teachers don't get enough money to what's it called? Live. And we think that we can pay teachers with just praise. I don't even do that with my dog very often. Sometimes I just don't have a cookie, and so I pay him with praise. I'm like, oh, good boy, give him the pets. But I make sure I don't do that very often. So before we start thinking about ourselves that we think education is important, recognize that we don't pay for it. Think about all the money that you're spending on this little endeavor, taking this class. In my world, free is not enough. I think this is a public good. I think what we are doing together is a public good. I think society will benefit from our efforts. I'm not sure that I could track exactly how that's going to work, but I truly believe that society will benefit from our efforts here today. And I question this every single day because that's the exhausting part. But I am continually convinced that society benefits from this thing that we do called education. And so with that in mind, free is not enough. People be walking around saying, I want to make community college free. Making community college free, making all higher education free still only benefits the wealthiest people. Because even if community college is free, you still got to pay to live. Free does not go far enough. I want to pay you to do this. If we want to play the capitalism game, that's one of the rules. You want people to do something, you pay them to do it. I want to pay students. I want this to be your job. I want you to spend time in the classroom, say, this is what you need to think about today when you're off of work. And then when you're off of work, I want you to go think about these things. I don't want you to have to think about, gosh, I wonder if I get to eat today. I wonder if I'll be able to pay the electricity bill. I don't want those things to be your concerns. And I'm willing to pony up the cash to do it. And I'm also willing to go around to people that aren't willing to pony up the cash and say, this is a public good and you are benefiting from this, Jeff Bezos, so pay up. Stop flying your dumb ass to space, pay up. Because that fortune isn't yours, it's all of ours. You built that on us. You know what I mean? Now thank us. But maybe I'm just a crazy person. Yeah, exactly. You're going to be transferring to a university. The university is going to be like, well, it costs $50,000 to go here. Is it because like calculus is like literally different at Harvard? I'm sure that the instructors are more professional because they can hire people to teach their classes for them, but anyway. See, instead of scholarships are a great idea, but instead of scholarships, I just want it to be your salary. Because here's another thing too. If you're just underperforming because you don't really want to be a student, I can just fire you and you can go do some other work. And then later on, you can just reapply. It's like, I don't think I'll try that school job again. Anyway. So what I want you to do is start with that catalog of surfaces. Start looking at the equation, everything's all blurry. Start looking at the equations and the surfaces. And this will give you an idea of what happens when x squared, combinations of positive and negative x squareds and x's, and what effect that has on the level surfaces. Then imagine those surfaces being slices of some solid. Start with that stack of paper. The level surfaces are the sheets of paper, and we're making a rectangular solid out of it. Imagine a solid cylinder. We can imagine that as a bunch of sheets of paper rolled into cylinders, cylindrical surfaces, and then just stacked up. Any questions? Comments? Snide remarks? So is C a value of Z on a plane? Yeah, the constant is going to be, when we're looking at level curves, we're making the Z a constant value. And then we're looking at the level curves, like looking down at the XY plane. From a level curve standpoint, since we're in three-dimensional space, we can always just make the X constant as well. And then we could see what the level curves look like looking at it, looking down on the YZ plane, or similarly, the XZ plane. So that's the other benefit that we get when we start looking at level surfaces. We can start thinking about level curves from other directions. Just like when we were looking at the elliptical paraboloid, looking top down onto the XY plane, we see a bunch of ellipses. But looking at it from the side, say looking at the YZ plane, we're going to be seeing a bunch of parabolas. Any questions? Is everybody okay? It only seems like it's a lot to think about because it's a lot to think about. The transition to looking at graphs of curves was easier because you've spent a lot of time doing it. And for the most part, we spend a lot less time looking at graphs of surfaces because it's always like always in the future. We start, oh, we'll look at that later. We'll look at that later. Meanwhile, we don't realize what makes looking at graphs of curves work is all the time we spend on it. So I'm wondering if there are ways we can introduce these three-dimensional graphs earlier. And I bet there are, but I might be just too old and dumb to think of them. Questions? Comments? Snide remarks? Oh, that's a great suggestion. GeoGebra is a good graphing calculator tool. So thank you for that reminder. "3D graphers are going to be a little bit finicky because you have to say where you want to look at it from. The fortunate thing is that we have a lot of experience from all of our, since we're doing a lot more 3D modeling of things, we have a lot of experience of how we can adjust where we're looking at it from, like click and drag. So they're getting better. It used to be that you had to type in manually where you want to be looking at your 3D model from. So to change where you're looking at it, instead of just like clicking and dragging it and moving it around, you kind of had to say, I want to look at it from the point 10, 10, 5. And then you have to adjust it by typing stuff in. But I don't think it's been that way for a long time. I think I'm just very old. All right. That's going to do it for today. It's really just me saying, hey, surfaces, look at a bunch of them. Start to make some connections. The reason that I kind of put this on you is that I can't make the connections for you. You have to get in there and start looking at them. Open up a 3D grapher like GeoGebra or Desmos and start graphing them and see what happens when you start changing what the constants are. All right, that's going to do it for today. If you have questions, stick around after the sign off, but that's going to do it for today. I will see you all on tomorrow when we're going to start talking about vectors, and so we can describe direction. Derivatives tell us what direction things are going. We need vectors to describe directions in three-dimensional space. All right, that's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing.